Hi, everyone. Welcome to lecture 3 of this workshop series. And today we're going to talk about geodesic convexity and general scaling algorithms. Okay, so today we're going to lay out the basic foundations for us to generalize what Akshay taught you in lecture 2 on scaling algorithms for commutative group actions, in particular for the matrix scaling problem. Okay, so all right. And the overview of the lecture today is in the first part, we're going to talk about Lie groups, Lie algebras, and positive definite matrices, which will give us the geometry of our optimization problems. And then we're going to give you a crash course on geodesic convex optimization. And then we're going to talk about a scaling problem for the, we're going to use the scaling problem for the conjugation action as a motivation to apply the geodesic convex optimization algorithms that we're going to have learned in part 2. Okay. All right. So let's go with a little bit of Lie theory, right? So you should think here in a high level that a Lie group is just a continuous group. Okay. Think of this group as the group GLN. Okay. The general linear group. And here the Lie algebra of the Lie group describes the infinitesimal action of the group near the identity. Right. So for instance, for the general linear group, its Lie algebra is the space of all matrices. And for the special linear group, its Lie algebra is the space of all n by n matrices, which are traceless. Okay. And here in this case of Lie theory, right, in the theory of Lie groups, we have that in our cases, right, in the case for GLN and SLN, actually this exponential map, right, which is given by the matrix exponential, right, which is like highlighted here. For us, for the cases that we're interested, like in this workshop series, the exponential map gives us a surjection, okay, from, for instance, for the set of all matrices to GLN, and in particular from the traceless matrices to SLN. Okay, so all right, so then if we look at the conjugation action, let's just use the conjugation action as our template example for today. Okay, and everything is a generalization of what we're going to see today for the conjugation action. So let's consider the conjugation action, if you remember, which we have our group is our general linear group acting on the space of n by n matrices, and the action is H is our group element, right? So this is in our group element, and A is in our vector space, right? So this is equal to V. So we take the element A to the element HAH inverse, right? The conjugation of A. And now, what is our optimization problem? If you remember our optimization problem, we can either say that it's the capacity problem or the log of the capacity problem, right? So this, we could call this the log capacity of A, right? So it's the log of the capacity. And this is the infimum over all elements H of the group G of the log of the L2 norm, right, squared of our group action here, right? And this is the Frobenius norm. So if you remember, the Frobenius norm of a matrix is just like, let me say square, is just the sum of the absolute values of the matrix squared. Okay, so this is the Frobenius norm. Okay, so we had this optimization problem. But now, if you think of the optimization problem, okay, and if you think of our function, if we call this function here, like just FA of H, right, because our variables are the elements of the group. Now, if we write this function FA of H, like this function is the logarithm of the trace, so this Frobenius norm squared, if I, let me put it here, so this is exactly the same as the trace of A transpose, right? So the Frobenius norm square is exactly the trace of A transpose. So if we write this function in terms of the trace, what we get is that FA of H is the log of the trace of, well, this is going to be our element A, and this is our A transpose. But now, if we make the transformation that H transpose H is equal to X, okay, then we have that our function FA of H is equal to this log of the trace of X, AX inverse A transpose. which really is just a function of this matrix X. But if you remember, if H is invertible, then the matrix X is a positive definite matrix. Right? So we turn our problem, which was a problem over an optimization over GLN, into a problem over optimization over positive definite matrices, right? So naturally we have that as, we can just consider this FA to be actually just f of A is a function from the space of positive definite matrices to the space of real numbers, right? Via this transformation. So, okay. Now you may ask, okay, what is so good about having a function from the space of positive definite matrices into the reals, right? Well, okay. It turns out that the manifold of positive definite matrices is a very special manifold, right? So we know that the space of positive definite matrices is a Riemannian submanifold of the space of all matrices. And what does this mean? This means that, you know, the set of positive definite matrices is a real smooth manifold, okay? Its tangent space is given by the Hermitian matrices, right? And the tangent space at every point is given by the Hermitian matrices. And it turns out that the positive the tangent space has an inner product, okay? Has a positive definite inner product. And what is the positive definite inner product on our tangent space? So our tangent space is an inner product space, with inner product being simply like the inner product of A and B is just equal to the trace of AB, okay? So, all right. So we know that P is a Riemannian submanifold, and moreover, in this manifold, okay, we have shortest geodesics, okay? So we can just write this as shortest geodesics. They are given by the following, the exponential map. So if I am at a point A, okay, so this, let's interpret what this means. So if I am at a point A of the Riemannian manifold, and I want to travel along direction Z. So A is in the positive definite manifold, and I want to travel along the direction Z. Now Z is a direction, so Z is in the tangent space of A, right? So Z is in the tangent space of A, but the tangent space of A, we know that is isomorphic to the set of Hermitian matrices, right? So Z is a Hermitian matrix. Then what is the element that I'm going to obtain? I'm going to obtain exactly the element exponential AZ, which is like simply say A half, right? A is a positive definite matrix, so it has a square root. And then we have a positive definite square root, right? And then we have the exponential map of Z. So this is the regular exponential map, right? So this is the matrix exponential. Exponential. And then I just multiply again a half. Okay, so these are the geodesics of in this manifold. And then to go from AB, the geodesic, okay, so the geodesic between A and B is exactly the geodesic given by this curve, like gamma of T, which is like A squared times this thing in the middle to the power of T times A squared. And you can see that gamma 0 here is equal to A, and gamma 1, what is gamma of 1? When T is equal to 1, what do we get? We get A half times A minus half times B times A minus half times A half, which is exactly B, right? So this is certainly a curve that goes from A to B, and it turns out that these are the shortest geodesics in the Riemannian submanifold, okay? Okay, and the metric here is just given by the inverse of the trace norm. So, but if you want to know more details, you can see the references in the workshop right up. Okay, and here the distance okay, between A and B is actually given by the logarithm of A minus the logarithm of B, and you take the Frobenius norm of that, okay? So this is the distance between 2 points and the Riemannian submanifold, okay? All right, so for this class, all we're interested is really on the forms of the geodesics. So we're just interested that the geodesics are given by this form, okay? And we don't need much more than that about the Riemannian submanifold, okay? All right, so now that we just gave a little very brief and bird's eye overview of Lie groups, Lie algebras, and the positive definite matrices, and we saw the geodesics, let's talk about a crash course on geodesic convex optimization, right? So, all right. So before we talk about geodesic optimization, or optimization over geodesics over the positive definite manifold, let's just review the standard convex optimization that you already saw a little bit, Akshay applying that to the matrix scaling problem, right? So we know that a univariate function, okay, so here we have a univariate function, univariate function, right? F is convex if and only if, when we take the second derivative of f, it's greater or equal to 0 for all elements over the reals. And we see that a function, a multivariate function, is convex if and only if the univariate restriction, okay, along every line, right, is convex for every vector A and B, right? So here in the multivariate case, like a function is convex if and only if the univariate restriction in any direction, sorry, oh, I don't know. Oops. So the univariate restriction in any direction, sorry for that, is convex, right? Like is convex in the sense of the first bullet, right? In sense of the first bullet. Okay, so in any direction and from any point, B, right, that we have there, from any point B, right? So, but now, and then we can also define, given a multivariate function, we can define the gradient of this function, right? And the gradient of f at a point A is the vector, which we denote by the gradient of f at A, in Rn, such that the inner product of fa times b, okay, is exactly equal to the partial derivative, to the directional derivative, right? So this is the directional derivative at A from direction B. Right? So the gradient is the vector such that if I take the inner product of the gradient with the direction of the derivative, we get exactly the value of the directional derivative, right? So, all right. And the Hessian of a multivariate function, right, is now the n by n matrix, which we represent by nabla square of f, such that if now we take the inner product, we take two directions, right? So we take two directions of derivative, B and C. We have that the inner product of C and the Hessian and times B is equal to the double directional derivative, right? Of the function A when I take a derivative first in the direction B and then take the derivative in direction C, right? So this is the Hessian And we also know that a multivariate function is convex if and only if this Hessian, okay, which is a symmetric matrix, right, like is positive semi-definite for all points in your domain, right? So, all right. And now that we have the definition of a convex function, let's talk a little bit about Lipschitz functions, smooth functions, and strong convex functions, which are kind of fundamental for giving some analysis on convex optimization algorithms, right? So we say that a map F from Rn to Rm is L Lipschitz if for all elements x, y, and Rn, we know that the norm of fx minus fy is upper bounded by this constant L times the norm of x minus y, right? And in particular, we call a function f to be L smooth if the gradient, okay? So if and only if the gradient is L Lipschitz, okay? So f L smooth if and only if like the gradient of f is L Lipschitz. Okay. So, all right. And now equivalently, a function is L smooth if and only if the Hessian, which is a positive, which is a symmetric matrix, is upper bounded, okay, in semi-definite, in the semi-definite order by L times the identity, right? So all eigenvalues of Hessian, and we know they're all real because the Hessian is a symmetric matrix, right? They're upper bounded by L. Okay. So, all right. And now we also say that a function, a multivariate function, is mu strongly convex if we take the Hessian, and now instead of the Hessian just being positive semi-definite, that was the definition of being convex. Now the Hessian is actually lower bounded. So all eigenvalues of the Hessian lower bounded by mu. Okay, so that's when we have a function being mu strongly convex, right? Okay, and mu is here is positive. Okay, we can think of mu being like non-negative just for avoiding trivialities. All right, and now now that we have the basic definitions of gradient, Hessian, and strong convex and smooth functions, let's see how we can generalize these definitions to the geodesic convex optimization setting, right? And for that, we need to recall the exponential map. So if you remember, the exponential map at A in the Riemannian manifold of positive definite matrices is just if I want to go from A in the direction H, right? Like, so if I go from A in the positive definite manifold in direction H, and remember that H is a Hermitian matrix, right? So we're going to write it like this. Then we take this exponential map of at A of H, which is equal to A half times e to the H. So this is the matrix exponential, just to recall, the usual matrix exponential, times A to the half. And what is the matrix exponential? Just to recap, e to the H is the identity plus H squared 2 factorial plus H cubed 3 factorial and so on, right? This is infinite series. Okay, so all right, and now we say that a function from the positive definite manifolds to the real is G convex, so it's geodesically convex, okay, which I'm just going to drop the G and say that the function is convex, but you know that when I refer to this function being convex, I mean that it's geodesically convex. If and only if the univariate function, okay, when I take the univariate function at T, and what do I mean by here? Like I just evaluate F at the x from A in the direction H, right? And I just take t like going in the line in that direction H, right? We know that this univariate function, note that f here is from, well, this f, this function GA, sorry, note that the function GA is a function from the reals to the reals, right? So our function f is geodesically convex if and only if this function, maybe I should say GAH, right? Like, so these functions GAH, let me just write GAH of t, right, is convex if for every A and H. Okay, so we say that the function f is geodesically convex if and only if the univariate function GAH is convex for every element of the Riemann manifold and every direction that we decide to go. Okay, so, and now how do we compute the gradient of a function from the space of positive definite matrices, right? So the gradient here, actually, if you remember, the tangent space at every point of the positive definite manifolds is a set of Hermitian matrices, right? So our gradient will also be, okay, a vector of the dual space of the Hermitian matrices, which if you take the dual, you can identify it with Hermitian matrices. So we're just going to say that the gradient here, okay, at A is the vector defined by this nabla F at A, is a Hermitian matrix such that the inner product of the gradient with the direction of the derivative is actually equal to the direction of derivative. Derivative at 0, evaluated at 0. Okay, so that's the definition. That's just the generalization of the definition of gradient, right? For the Riemann manifold, and the Hessian is the same, right? So the Hessian of F here is the matrix, which is we denote by nabla square, which now is in the space of Hermitian matrices, tensor the Hermitian matrices, such that now when we have, and again, I'm just identifying the Hermitians with the duals, okay, such that now when we take, to be more proper, we would have to do like Hermitian tensor, maybe like this dual. And now such that when we take the inner product of F, when we take two directions of derivative now, right, like F and H, and we take this inner product with the Hessian, what happens is that we get that this value is exactly the value of the direction of both directional derivatives, like of the double directional derivative in the directions F and H. Okay, so this is the same generalization that we had for the usual convex, the Euclidean convex case. Okay, so all right, and now what do we say? We say that a function in the positive definite manifold is geodesically convex if and only if the Hessian, okay, is positive semi-definite for all matrices in the positive definite manifold. Okay, so again, this is just the same generalization of the two definitions of geodesically convex. Okay, so all right, but notice that we're transforming, like the condition of being geodesically convex reduces to the definition of being just convex, just regularly convex for univariate functions, right? So, all right. So, all right, and now that we defined geodesically convex functions, we can talk about smooth and strongly geodesically convex functions. And again, we can use the definition of the Hessian to say that a function f from the space of positive definite matrices is L smooth if and only if the Hessian is upper bounded by L times the identity. And we can say that the function is mu strongly convex, again, if and only if the Hessian of our function is lower bounded by mu times the identity. Okay, so all right, so now that we know these definitions of geodesically convex and geodesically strong convex and geodesically smooth, right? We can try to do the gradient descent for geodesically smooth functions. So how would gradient descent for geodesically smooth functions work, right? So here's our problem. So our input here is a geodesically convex L smooth function, okay, f, and we have a parameter epsilon, which is our approximation parameter, and an initial point in the positive definite manifold. And now what we want to output is to find a point B in the positive definite manifold such that the gradient of our function f at B is less than or equal to epsilon, right? That's the usual gradient descent. And here we're just doing the geodesically convex gradient descent, right? And now what do we do? Well, start with our initial point A naught equals to A, and let's set the parameter eta, right? Like the learning rate to be like less than 2 over L. And now you can pick any of these parameters, which is less than 2 over L. And now what do we do? Let nabla k be the gradient of f at the point ak, at the kth point of your iteration. Now, if the gradient is large, is bigger than epsilon, what do? Well, we just let the new point, right? So this is the next point of the iteration, next point of your iteration, to be, well, if you remember from the gradient descent, what does gradient descent do? Well, the gradient descent takes xk plus 1 to be equal to xk minus some eta times the gradient at the direction at time k. So this is the regular gradient descent, like the convex gradient descent, right? So this is convex gradient descent. But here we cannot do that because we're in the geodesically convex setting. But then how do we take the next step, right? So the next point of the iteration, I just use the exponential map, right? Use exponential map at A, okay? And in which direction? In the direction of the gradient, right? And what is the next iteration? We just use eta as the learning parameter, the same way that we used for gradient descent. So essentially, gradient descent for geodesically smooth functions works in exactly the same way as it does for the convex setting, for the Euclidean setting. But now the only thing that we need to replace is, instead of having because this guy here is the geodesic in the Euclidean setting. So all we need to do is to replace this by the geodesic in the Riemannian setting, right? So, and then here is the geodesic in the Riemannian setting. So geodesic in the PDN setting. That's the only modification that we need to do gradient descent for geodesically smooth functions, okay? And now the analysis of the geodesically gradient descent is the same analysis as for the convex case, okay? And if you want to do this, you can just do this as a practice problem, right? So as a practice problem, do this. For those of you who were like acquainted with convex optimization, right? So as a practice problem, do this, show this. Okay. Okay. And now that we know how to do geodesic gradient descent, let's see how to solve the scaling problem for the conjugation action using optimization techniques, the optimization techniques that we just learned.